Okay, and I wanted to say about the test. I think I asked for the exact answers on those things, and if it comes out to be a big old natural log answer thing, then give me 2 decimal places though. but if you don't,
should I do both just to be safe?
yeah, do both. If it comes out to 3, obviously you don't have to. The answer's 3, you don't have to give me a 2 decimal place approximation. But, so, if it comes out to a big old natural log thing or e to something, yeah. All right, so this is exponential growth and decay models, and we just did a problem like this. This is the mathematical model for exponential growth or decay, and it's A equals A0 e to the kt. A0 is the initial amount at time t equals 0. T equals 0. A0 is the original amount or size of a growing entity. If you've got k greater than 0 in this equation, then you have a growing entity. A0 is the original amount or size of the growing entity at time 0. That's why it has a 0 subscript. A is the amount of time t, and k is a constant representing the growth rate. If k is less than 0, then the function models the amount or size of a decaying entity. A0 is the original amount or size at time t equals 0. A is the amount of time t, and k is the constant representing the growth rate. So here's an example. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. We wanted to keep this in the same units, because that's why we didn't say 1.052 billion, or we didn't write it in billions or something. We're going to use the exponential growth model, in which t is the number of years after 2000, to find the exponential growth function that models the data. We're going to round k to 3 decimal places. So, if you're going to start at 2000, then t equals 0 in the year 2000. So our A0 is right up here. It says in 2000, the population, so this is our original amount at time t equals 0, 807 million. So our original function is A equals A0 e to the kt. But it gives us what A0 is 807. So A is 807 e to the kt, because that's the original amount, 807. And then you look at the other information it tells you. It says by 2011, so that would be t equals 11 years after 2000. It had grown, so our A will be 10,052. We can use this information in this equation. We're given all the values except for k. We're gonna substitute those in. 1052 equals 807 e to the k and times 11. T is 11. Now we can solve this just like we did the other equations. We're going to isolate this part, so we're going to divide by 807. we're multiplying by 807, we're going to divide by 807. Now I just want to write e to the 11k over here equals, and I'm going to leave space for natural log. So we got an e to the something equals this divided by that. We're going to take the natural log of both sides. We have a single exponential on the left, e to the something. Natural log will undo that, and then we get 11k equals natural log of 1052 divided by 807. And then divide by 11. So this is what k equals. We need 3 decimal places, so we need to put that in our calculator and get it to 3 decimal places. Turn it on, do natural log of 1052 divided by 807 divided by 11. So I had to close the natural log, and I get 0.024. So now I can write a general equation and answer the next part. So my general equation, number 3, write a general equation for Africa. But this is for Africa. You want just an A equals 807 e to the 0.024 t. So this is for Africa. The growth equation for Africa. A general one where we could put in any t and find an a, or put in any a and then solve it algebraically and find t. So, in which year will Africa's population reach 2,000 million? We have to use 2,000 million because this equation was in millions. So that's why we got 2,000 million here. We set, that's our A, and now we want a T. And then we convert that to a year. The year will be 2,000 plus T because we started at 2,000. So here's our equation. We set, that 2,000 is the year because we started in 2000 up there. Okay, there's a couple 2000s here. Okay, so we got, here's our equation. We got A is 2000 equals 807 e to the 0.024 t. We can solve for t. We get this by itself, so we divide by 807. We have e to the 0.024 t equals 2,000 divided by 807. When we take the natural log of both sides, that cancels. Okay, and we're going to divide then. I'm tired of writing all this out. So by 0.024. This is t. So it's going to be the natural log of 2,000 divided by 807, close the parentheses, divided by 0.024. And t is approximately 37.8. Then we can round to the nearest number. T is 38. And we're going to add the 2000 because that's what t equals 0 was. That's t equals 0 was at the year 2000. So in the year 2038, the population will reach 2 billion. The population of Africa will be 2 billion in 2038, the year. Africa. Okay. We'll get the calculator out of the way. Okay, so that is the exponential growth and decay models. And I really just asked you about growth on these. I haven't thrown in decay. I don't think. Okay. But decay just means that K will be negative. It works the same way. Like half-lives. All right, is everybody done writing? No. So we'll leave that up. So here's the logistic growth model. This is a mathematical model for limited logistic growth, and it's given by this. And as long as this is a 1 here, and that's what it is on all my stuff now, we have a 1 here. Since we have a 1, the limiting size as long as we have a 1 down here, got a 1. 1 plus a e to the minus bt. The limiting size will be the constant in the numerator. It will always be the limiting size as long as there's a 1, and there will be a 1 there. Right here, the limiting size is always c. So here's an example. Notice it has a 1 in it. So in Learning Theory Project, psychologists discovered that f of t equals 0.8 divided by 1 plus e to the minus 0.2t. It's a model describing the proportion of correct responses, f of t, after t learning trials. So find the proportion of correct responses prior to learning trials taking place. That means t equals 0. So we just want to find f of 0. You can put it in your calculator, but at least write down the equation and show that you're plugging it in. When you put it in correctly, you're going to have 0.2 times 0 is 0. You're going to have e to the 0. This part, e to the 0, will be 1. So you're going to have 0.8 over 1 plus 1. 0.8 divided by 2 is 0.4 or 0.40, 40%. It's the proportion of correct responses. In a percent, it means that people would be getting 40% before the learning trials took place. They took a test without studying, or even going to class. Okay, find the proportion of the correct responses after 10 learning trials. They just want t equals 10 Can you put this in the calculator correctly? 1 plus e to the negative 0.2 times 10. And you do need parentheses around there. If you leave parentheses off, you can get the wrong answer. So 0.8 divided by parentheses, 1 plus second natural log negative 0.2 times 10. Close the parentheses, or the calculator would have closed it. And there it is after 10 learning trials. We're at to two places we're about 0.70 or 70%. Okay, so, and the last question says, what's the limiting size as continued trials take place? And you can put it in your calculator, you know, y1 equals 0.8 divided by parentheses 1 plus e to the negative 0.2 times x. And then we'll graph it and use trace. But you do need to change your window. You may need to change the window. Well, I'll go ahead and do that. But the limiting size is going to be 0.8 or 80%. So y equals clear 0.8 divided by parentheses 1 plus second e to the negative 0.2 times x, close the parentheses, there we go. We can hit graph, and we're really not seeing a lot. Why are not we seeing a lot? Because what are we getting out of this thing? Percent. We have to change our window. We're getting out. We're getting numbers between 0 and 1 out. And so we got to change our window for y. We're getting 0 to 1. So we can make x go up to 1,000, say, and the scale be 100. But y, oh my gosh, look at the y. No wonder we couldn't see anything. Y needs to go from 0 to 1, and maybe we'll have the scale at 0.1. Now we can graph it. Okay. And then if we hit trace, this is the limiting size. We're way out here. We had to put huge numbers for x in, but we had to change the window to even see it. But as long as this is a 1 here, the limiting size will always be 0.8, or whatever this is. So the limiting size inside our calculator is 0.80 or 80%. It will always be C as long as you got a 1 there. Okay, so that's the limited logistic growth model. And I'm going to skip. This is good for physics. Do you guys have to take physics?
Yes, but I don't want to learn it right now.
If you don't want to learn it now. So I have it worked out. It's Newton's law of cooling. Here's the thing, and you have to identify everything, put everything into the original equation, solve for your K like we did before, which is forward us to write a general equation. And then it asks some questions, and you can use that general equation. And then when will the temperature be 35, and then you solve it logarithmically. So this is posted as a build-in note.
Is this all MATLAB? You know?
I hope not.
I don't think so. I think I got rid of it. I almost thought about getting rid of this page. But don't tell the physics people that. No, I don't know. Almost got rid of that page in the notes. But this is on the test, this last thing. So we're going to express an exponential model in base E. This is a plain old exponential equation, and we want to write it in terms of base E. And this question is on your test, and maybe on the final. Okay, so remember we could cancel out when we had E to the natural log? Well, we could also just throw those in there. So we've got y equals 4 times 7.8 to the x. This is our original base, but we like base E rather than base 7.8. So how are we going to change this to base E? We're going to insert an E to the natural log, and then this brings this up here. We inserted E to the natural log. We can insert this as well as cancel it out. So we inserted this. It brought this stuff up into the exponent. And then we're going to use the product rule and bring the x out front. E to the x times natural log of 7.8. And then we really don't like to write our equations that way. We like to write them with the x last. It is natural log of 7.8 times x, so we have to put parentheses around here because x is not inside our natural log. And this is the exact answer in terms of a natural log. This is y equals, this is the exact answer. And then we want, and we will never get a number for an answer here. We're just changing the looks of an equation to be e to the something instead of 7.8 to the something. So now we just, the directions, I tried to fix them, but these directions say, and then round to 3 decimal places. No, you're rounding the natural log to 3 decimal places. And I think I specifically put that in your test. So you go into your calculator, second quit, and do natural log of 7.8. And write it to 3 decimal places. So natural log of 7.8 is approximately 2.054. So what we want, what this question wants, is the approximate answer is y equals 4e to the 2.054 times x. This is the approximate answer. This is your exact answer, and they're both equations. You're not given an x, you're not going to come up with just a number. And so that's the end of 3.5. Do you want to do the Socrates quiz so that it's not due Monday and you don't get 100 times?
Yeah.
Okay. All right. We're going to go into, I'm going to go into Socrates. Okay. This, you can look at the quiz here. These are the questions. You can look at your quiz, but I'm going to go into Socrative and actually. I need to stop. There it is. Okay. We'll just do a quick. We're going to do solving exponential and logarithmic equations. And I do want you to get instant feedback. And you can see your final score, but everybody that's here today just get 100 on it. Did somebody leave though?
Yeah.
Well, everybody that's still here at this point in time will get 100 on it. Anybody that left? Well, yeah, okay. So, it's going to show you your score, but don't worry. Let's see. It's going to be, you guys can do this. Okay. Go into YNZKGECN. And you don't have to use your real name if you don't want to. Or I'll make sure, I have to write this down. And then I'll get off of it. YNZKGECN. You have to go to Socrative.com and join this quiz. That boy. Okay. Join this quiz. And who was it that didn't have a date on Valentine's Day? I felt so fired. Somebody wrote down as their nickname on something. I don't know. It's Valentine's Day. Don't have a date on Valentine's Day. One of our nearpods. Oh dear. Okay. And I can even join it, but no, I don't want to. Okay. And it's going to give you feedback and tell you if you're right or wrong, and it's more of concepts. Did you get the concepts of section 3-4? And it's going to give you feedback.
Yes.
Everybody else can.
Yep.
And solving, you're all doing it. You finished?
No, not yet.
Oh, well, you're going to write it out.
Yeah, I'm not ready.
That's a good idea. Good. Important to understand it.
Well, I don't
Socrative.com. It's important that you understand this so that you can do it. Oh, is it stage? Are you done?
No, it's still terrifying. I don't like that show.
Did
It gives
you-
me nightmares. His name's Bernie?
Yeah, that's right.
My cat's name is Bernie.
Did you do
Like
it
burnt
already?
toast.
Did you answer any questions? Why did you do that? Oh, okay, well, maybe you should try to.
What? You just call him His name's Bernie.
Did you talk to Wyatt?
Yeah, like Bert. He's such a good cat.
Yeah, it doesn't matter, no.
He's drinking that stuff over the table. I feel like my face is red. Yeah, it's
Did you do it? Are you on there?
Yeah, I'm here.
Oh, okay. That's right, it's working on it, device. Now it's working. Okay. So it's important that you understand this concept. And this is, what's the first step, the second step? Yeah.
And we're stuck on. What do we need to do for
Because you're supposed to.
Condense
outside of it.
completely. You're gonna pull it up and put it in there.
Because you're adding it.
Then we get rid of those. Yes, you have to pull these up here. And now you can condense, and it's gonna be, what is 2 to the 7th times, whatever that is, to the second.
I don't either.
Okay.
I don't serve catch.
Yeah,
I'm not a waiter.
right, and then you're gonna,
Log.
Oh, look, you you move it to the X.
I have to do like very specific steps.
okay, right.
It's still reading my thoughts. I'm
They're
turning
both
it.
the same.
And you're over here saying.
So they're the same base, so.
So,
Just multiplying them.
multiplying because of the plus sign.
Yeah.
Okay. I think.
And there you have
I
it.
think.
And that's all inside the log, so I would put it
From my
in a
educated
bracket or
guess, I
something around the whole thing.
Another
For parentheses, yeah,
No,
yeah,
because
that's all inside
those
the
are
log.
exponents
That's
now.
all basically needed.
Yeah.
Wow. Okay.
But it also
I
could
didn't know
be.
that was going further than that.
No, I think it's.
Okay. If anybody needs help, are you getting these?
Oh, look,
Are
told
you
you.
working those
I
out?
told you.
She got it right.
I did get it right.
Good job. I'm not surprised, you're good.
Thank you. There's pass us too. Okay. Now I think it's red.
So these are the concepts that you need to know in order to solve these equations correctly.
Should have.
And if anybody has any questions, let me know.
It's like those correct answers. Huh?
And the one that has, does that have 2 answers?
Yeah. There's two.
Okay. Well, you can also raise both sides of the equation to the same exponent. And
I don't
then
think it matters.
so, guys, you can raise both sides of the equation to the same exponent also, besides taking the natural log of both sides or log of both sides. So, let's see, do I have somebody's test?
We're trying our best.
All right, well, I'm going to stop the recording.
So hard on yourself.